Hello and welcome to a flip session on how to draw Lewis structures. Should be a pretty quick one. A couple of quick rules to follow maybe as you learn to do Lewis structures, and then once you have practiced a few here and there, you'll probably kind of develop your own techniques for doing this, but I wanted to kind of lay out some of the basic ground rules and suggest a few techniques, and then you can work on them, practice them, and kind of develop your own style. A couple of things early on to kind of be aware of. Really, one of the primary things is to pick up on the first two rules here. One, that you really do need to determine the number of valence electrons, and then two, that you really do need to be able to draw the skeletal structure of the atom accurately. And most of the time, the valence electrons should be easy. It's a little sad when people need to use a calculator to do that, but so be it. Second thing is that the central atom in the structure is usually the one written first in the formula, and by convention, formulas are written so that the less electronegative or least electronegative element is written first. And practically what that usually means is that more electronegative elements are surrounding it, trying to take its electrons, and usually if it's a covalent bond, it's electronegative enough to not actually lose those electrons. And so the atoms end up bonded together, but with the less electronegative one trapped somewhere in the middle. So those would be the first couple of steps. First, figure out how many valence electrons you have to use. It's really a good way to lose most, if not all, the points on a Lewis structure problem if your structure doesn't even have the right number of electrons. That's sort of an unforgivable mistake. It should be an easy thing to calculate. Secondly, draw the skeletal structure, put the central atom in the middle, arrange the other ones around it. It really doesn't matter how you arrange them in your drawing. I don't care if they're 180 degrees apart, 78 degrees apart, whatever. Thirdly, you want to connect those atoms with single bonds. You know they have to be bonded to each other. If they're not bonded to each other, you don't actually have a molecule. So you have to essentially take care of that. Then once you do that, one way to sort of test it is just begin to put electrons around all of the atoms. Start with the outer ones, the peripheral ones first, and then fill the energy level requirement. So if it's almost every atom, that'll get you to 8. If it's something like hydrogen that only needs 2, well, you're pretty much done once you've bonded it one time. So fill in the number of electrons that you need. Then you can fill in the remaining electrons on the central atom. At that point, it's not bad to then see, have I used all of my electrons? If I had 20 electrons, did I use 20? If I had, 16 electrons and I've tried to use 20, what's the problem here? Or if I have 16 electrons and I've only used 12, well, I've got 4 left over, what am I to do? Well, if you have extra electrons left over, you should put them on the central atom. The chances are very good that the peripheral atoms, being more electronegative, will take a certain number of electrons, fill an energy level, and that'll be that. The central ones, being less electronegative, are sort of the victim in our anthropomorphization of the elements, and they may well end up with some extra electrons around them because they're not willing to let go of their own electrons, but they also have their electrons being sort of shared from the atoms around them, so they end up with perhaps more than 8. So if you have extra electrons left over, put them on the central atom. If you have the reverse problem that you don't have enough electrons to complete step 4, use double or triple bonds, and you can kind of go step by step and see, if I use 1 double bond, does that fix the problem? Do I need 2 double bonds and or a triple bond, etc.? And what we'll do is look at a quick example here for CO2, and I'll leave you with something to maybe consider as you go through this. So CO2 has 16 valence electrons, 4 for the carbon, 6 for each of the oxygens. Connect them with single bonds, as you can see here. And then when you add in all the electrons around the atoms here, you'll notice that that leaves you with a requirement of 20 electrons, and you only have 16, so that's not going to get the job done. So we're going to need some multiple bonds. Now, we had a double bond here instead of the single bond. Well, that fixes a little bit of the problem. So now instead of requiring 20 electrons, we're going to require 18. We again still only have 16, so we'll have to try again. 2 double bonds gets the job done, and that's that. Something to consider, though, is wouldn't a triple bond achieve the same thing as well? So couldn't we have done something like this? And if we had done that, and I'll try to draw these electrons in here a little bit. If we had done something like this, doesn't this take care of the octet rule for everything? The oxygen here on the left has 8 around it, 6 from the bonds here, 2 more there, that's 8. The oxygen over here has 8, 6 of its own electrons here, 2 more in the bond there, and the carbon has 8 as well in the form of 4 bonds. So it certainly satisfies the octet just as well as the conventional structure, so why don't we see this particular one? And that'll be a topic that we'll pick up, and there's certainly laboratory evidence indicating which one is correct. But there's also ways that you can assess whether it's correct or not using some fairly common sense chemical applications of what you know already. All right, a quick session. Hope you've learned a little bit about Lewis structures, and the big key really is just to practice them, and we'll get plenty of practice in over the next couple of weeks.